From Stardust to Worlds, the cosmic beginning GIF, we trace the story of planets back to its first chapter. We find ourselves long before any planet existed, in a universe still too young to know complexity. In the first 3 minutes after the Big Bang, matter cooled just enough for the simplest nuclei to form. Hydrogen and helium flooded space with a whisper of lithium. There was no iron, no silicon, no oxygen to build oceans, mountains, or the steel in our cities. Those heavier elements were not given, they had to be made. They were forged later in stars by the pressure of gravity and the fire of fusion, and dispersed by stellar winds and supernovae. Only after multiple generations of stars were born and died did the universe become seeded with the ingredients of rocky worlds. Planets are not the default state of the cosmos. They are the children of starlight and time. This enrichment created diversity. Carbon and oxygen would later combine into ices and minerals. Silicon and magnesium would harden into silicate rocks. Iron would sink to the cores of growing worlds. We call all these elements metals in astronomy, even though many are not metals in chemistry. The metal content of a cloud, its metallicity matters. Higher metallicity increases the supply of solids, accelerating the growth of small seeds into planetesimals and then into planets. That is why the oldest stars, born when the universe was poor in metals, are less likely to host rich families of planets. With each cosmic generation, worlds became easier to build. Gravity threaded this whole story together. When massive stars exploded, their shockwaves compressed nearby gas, stirring turbulence, creating knots in the interstellar medium. These knots-gent molecular clouds were cold enough for hydrogen to pair into molecules and for dust grains to survive. Within them, gravity could overcome pressure and trigger collapse, birthing new stars. Because the collapsing cloud had some initial spin, conservation of angular momentum flattened part of the infalling material into a rotating disk. That disk thin, dusty, and warm near the star, but icy and cold beyond, was the cradle of future planets. From the beginning, heat sculpted possibility. Close to the young star, high temperatures destroyed fragile ices and drove off volatiles. Only refractory materials, metals, and silicates could survive to condense. Farther away, in the cool, shadowed reaches of the disk, water, carbon dioxide, methane, and ammonia froze onto grains. This invisible boundary called the snow line drew a chemical map across the disk. Inside the line, dry, rocky ingredients. Outside, an abundance of ices that dramatically increased the mass available to build cores. The fate of future planets followed the thermodynamics of their nursery. The earliest solids to condense in our own solar system left fingerprints that we can still hold in our hands. Primitive meteorites carry calcium-aluminum-rich inclusions. K and once molten chondrules, tiny beads of rock that cooled quickly in the nebula. Radiometric dating shows that K formed about 4.567 billion years ago, marking the solar system's birth certificate. Chondrules followed in the next few million years, like sparks in a protoplanetary foundry. Every pebble that ever rained toward the sun, every boulder that drifted outward, every grain that stuck instead of shattering, contributed to the slow construction of worlds. Between stars, ultraviolet light and cosmic rays chased chemistry into surprising corners. On the surfaces of dust grains, simple molecules assembled into more complex organics. Ices trapped volatiles and preserved them for delivery to young planets. Comets and carbon-rich asteroids became couriers of carbon and water, a cosmic logistics network that would eventually inventory Earth with what it needed for oceans and perhaps the chemistry of life. The phrase "we are stardust" is true, but incomplete. We are also ash from supernovae, frost from the edge of disks, and dust that once drifted in the light of a newborn sun. Disks and dust, the engines of accretion around a forming star. The protoplanetary disk is a cosmos in miniature. It has weather and climate. It has storms where turbulence lofts grains, and doldrums where particles settle into the midplane. At the smallest scales, Micron-sized grains collide gently and stick through electrostatic forces, forming fluffy aggregates like snowflakes in microgravity. As particles grow, their dance changes. Collisions become rougher. Some aggregates compress and cling, others splinter and erode. The balance of sticking and shattering defines the pathways from dust to pebbles, from pebbles to boulders, and from boulders to kilometer-sized planets. There is a problem known as the meter size barrier. In a gas disk, meter-scale rocks experience strong drag and spiral inward toward the star in a few hundred orbits far faster than they can grow by pairwise sticking. Nature needed a shortcut. One such shortcut is the streaming instability. In regions where pebbles concentrate, their drag on the gas slows the gas locally, which in turn reduces the head wind on the pebbles. Pebbles clump, their density rises, and gravity can take over. In a geological eye blink, loose swarms of pebbles can collapse directly into planetesimals tens to hundreds of kilometers across. This top-down route avoids the meter-size trap and populates the disk with large building blocks quickly. Once planetesimals exist, gravity becomes the architect. The largest bodies grow faster because their gravity focuses incoming projectiles, increasing collision rates. This is runaway growth. A few dozen or a few hundred bodies in each annulus of the disk become oligarchs, regional lords, whose gravity dominates their neighborhoods. They stir smaller bodies, exciting their speeds, while sweeping up what they can. Some collisions are gentle mergers, others are hypervelocity demolitions that create debris disks of fine dust. ALMA has imaged such rings and gaps around young stars, ghostly signatures of unseen planets sculpting their birthplaces. The disk itself pushes back. Gas orbits the star slightly slower than Keplerian speed because it is partially supported by pressure. This creates a head wind on solid bodies. Pebbles drift inward toward regions of higher pressure, often piling up at pressure bumps created by magnetic effects, temperature transitions, or the edges of gaps carved by infant planets. These pressure traps act like conveyor belts and collection bins, channeling material into zones where cores can grow rapidly. Accreting pebbles is vastly more efficient than relying on rare, violent mergers alone. Temperature gradients and chemistry add further structure. The water-snow line is the most famous, but similar lines exist for carbon monoxide and carbon dioxide. Ices. Each snow line marks a jump in the available solid mass and a change in the stickiness of grains. Near snow lines, sublimation and recondensation can concentrate solids and promote rapid core growth. In effect, the disk draws invisible circles on itself, and planets tend to prefer those circles when choosing where to be born. Magnetic fields, ionization, and radiation sculpt the disk's lifetime. Stellar winds and ultraviolet light peel away gas from the surface. Photo-evaporation opens holes that spread and widen. Viscous processes redistribute angular momentum, allowing gas to drift inward and accrete onto the star. Observation suggests that most disks disperse in 2 to 5 million years. That is not much time. Giant planets must assemble their massive, gaseous envelopes before the gas is gone, and rocky planets must complete the bulk of their growth while the traffic of planetesimals still delivers raw materials. Planet formation is a race against the evaporation of its nursery. Building the rocky planets, heat, violence, and digging inside the snow line. The ingredients are dry, silicates, metals, and a whisper of refractory compounds. Here, terrestrial planets take shape. After oligarchic growth, dozens of Moon, too, Mars-sized embryos share the inner disk with swarms of smaller planetesimals. Their orbits are initially nearly circular and coplanar, but mutual gravitational tugs slowly increase their eccentricities and inclinations. The system approaches instability. Over tens of millions of years, close encounters trigger a storm of giant impacts. Worlds collide, worlds merge, worlds shatter. Earth's own history bears the marks of this violence. The leading explanation for our moon's origin hydrogen impact hypothesis, a Mars-sized body, often called Theia, struck the proto-Earth in a glancing blow. The impact vaporized and ejected material that soon assembled into a disk around Earth and then into the Moon. The chemistry and angular momentum of the Earth-Moon system make sense in this scenario. A catastrophic collision, rather than being a rare accident, may be a common feature of terrestrial planet assembly, while collisions sculpt the exterior architecture. Heat reshapes interiors. Accretion releases gravitational energy, short-lived. Radioactive isotopes, such as aluminum-26, add additional heat early on. Many embryos became global magma oceans molten from surface to depth. In these oceans, iron-loving elements sank, assembling dense metallic cores. Lighter silicates remained above, forming mantles and early crusts as the surface cooled. Core formation created planetary dynamos, convecting, spinning cores that generate magnetic fields. A strong magnetic field, like Earth's, can shield a planet's atmosphere from erosion by stellar wind, an essential defense for long-term habitability. Water delivery to the inner planets, a subtle chapter. Inside the snow line, water was scarce, yet Earth is blue. One pathway involves the delivery of water-bearing planetesimals from just beyond the snow line, carbonaceous chondrite-like bodies nudged inward by resonances with the forming giant planets. Another pathway uses pebble accretion. Icy pebbles drift inward and either sublimate near the snow line, enriching the local gas with water vapor, or survive long enough to be incorporated into embryos. Isotopic fingerprints, such as the deuterium-to hydrogen ratio in Earth's oceans, act as clues to this delivery history. The answer is likely a blend of sources and processes rather than a single silver bullet. Atmospheres arise and evolve alongside surfaces. Early atmospheres can be captured directly from the nebulae, for rocky core grows quickly enough while gas remains. More commonly for terrestrial planets, the first atmospheres are secondary, exhaled by volcanoes and impacts. Carbon dioxide, water vapor, nitrogen, sulfur compounds. As the surface cools, water condenses to oceans, and carbon dioxide dissolves in rain and rocks, creating climate feedbacks. On some worlds, like Venus, greenhouse heating drives a different fate. On others, like Mars, small size and weak magnetic fields invite atmospheric loss. The delicate balance between gravity, outgassing, solar radiation, and magnetic shielding dictates whether a rocky planet keeps a sky and what that sky contains. As chaos waned, the inner solar system settled. Mercury, perhaps the survivor of mantle-stripping collisions, kept an oversized iron core. Venus became a greenhouse world. Earth stabilized with a large moon, a magnetic field, and surface water. Mars lost heat, froze its magnetic dynamo, and thinned its atmosphere. The asteroid belt never formed a planet. Jupiter's early presence may have stirred and starved it, preventing a single dominant embryo from sweeping it clean. The leftovers became a catalog of time capsules. Vesta with its basaltic crust, Ceres with hydrated minerals and possible brines, and countless smaller bodies that still carry the chemistry of the solar nebula. Birth of giants and the era of migration beyond the snow line. Everything scales up. Pebbles are more massive because they carry ice mantles. Cores can reach 10 Earth masses quickly if they reside near pressure traps or snow lines. Once a core becomes massive enough, it perturbs the gas disk strongly. A shock forms ahead of the core. Gas piles into a circumplanetary disk that will later birth moons. If cooling is efficient, the core's atmosphere contracts and fresh gas flows into replace it. Runaway begins. In a few 100,000 to a few million years, a gas giant's envelope can balloon to many times the mass of the core. The result is a planet that glows with leftover heat, radiating more energy than it receives from its star during its youth. But giant planets rarely stay where they were born. As they interact gravitationally with the gas disk, they exchange angular momentum and drift. Lower mass planets carve shallow wakes and undergo Type 1 migration, often toward the star. Massive planets that open deep gaps in the disk migrate more slowly in the Type 2 regime, locked to the viscous evolution of the gas. The direction and speed of migration depend on local temperature gradients, opacity, magnetic fields, and the disk's turbulent structure. This is not tidy clockwork. It is fluid dynamics at astronomical scale. Our own solar system likely experienced dramatic migration episodes. In the Grand Tack hypothesis, Jupiter formed beyond the snow line, but then migrated inward to about 1.5 astronomical units before reversing course when Saturn reached a resonant orbit. This tack could explain the low mass of Mars and the depletion of the asteroid belt, sculpting the inner system. Later, in the NICE model, rearrangements among the giant planets destabilized planetesimal reservoirs, driving an outward migration of Uranus and Neptune and triggering a spike in impacts across the solar system. These models are not final truths, but they demonstrate that migration and chaos are part of how planetary systems mature. Exoplanets showcase migration's extremes. Hot Jupiter's gas giants skimming their stars in orbits of just a few days almost certainly did not form where we find them. Some likely migrated inward through disk interactions. Others may have been kicked onto eccentric or inclined orbits by distant companions and then circularized by tides. Compact systems of super-Earths and mini-Neptunes crowding close to their stars may be the products of migration plus in situ growth. The lesson from thousands of exoplanets is clear. The architecture of planetary systems is not a fixed blueprint, but a living, shifting arrangement shaped by forces both gentle and violent. Moons, rings, and magnetospheres grow alongside giants. Circumplanetary disks accrete and spread like miniature solar nebulae. In these disks, pebbles and moonlets collide and assemble the regular satellite systems we see around Jupiter and Saturn. Some moons capture oceans, others become volcanic or icy. Magnetic fields trap charged particles and paint or auras across polar skies. Rings weather from embedded moonlets, captured debris, or the grinding of icy particles trace a balance between gravity and fragility. A giant planet system is a solar system in microcosm with its own meteorology, geology, and kinship dramas.